Hi everybody, welcome back. So this time we'll be talking about the direction of a vector. So a lot of times you'll be like, well, why isn't it just going to be given to us in the Cartesian form? Short answer, no. It's not going to be given in the Cartesian form most times. Maybe one of the vectors will, but you might also get something where it gives you these angles to each of the axes. So these are usually termed alpha, beta, and gamma. And they help us get our direction cosine, which we're going to learn about in a minute. Now, all these angles are measured from their axis. That's the important thing. They're not measured from some perpendicular perfect thing. They're measured from the axis that they care about. So one of them goes to the x-axis, one of them goes to the y-axis, one of them goes to the z-axis. You can see that here. And it's not always easy to tell in a problem state when you're looking at it. I try to make it obvious, but if it's not, ask. If you get on an assessment and you couldn't tell one way or the other, email me and I'll see if I can't give you another problem. But email me at the very beginning. Don't try for 30 minutes, get it wrong, wait 2 hours, and then email me. I'm not going to do it then. I need to know right away. But it should be obvious. If you see alpha, beta, gamma, there it is. Okay, so with that, these angles, they're from your vector to the axis that you care about. Now, how do you do this? What's so important about this? Well, if we look at just that axis and just your vector, we can create something called direction cosines, okay? These direction cosines are very, very important. Now, why are they important? What's so cool about them? Well, what's cool about them is that because, I'm going to pull out this one right here, this little triangle right here. Okay. This isn't super easy to see. But if I look at this little triangle right here, what happens is that vector, which is now 3D, becomes sort of 2D in this not quite perfect plane. So the bottom axis is the y-axis. This is the y-axis, and this is just some kind of crazy axis. But this happens to be a right angle. So this is my vector, let's just call it A. This is a right angle, and this is my direction cosine. Okay, you're like, this intrigues me. Well, all you care about is you don't care about this crazy thing. That's not important. That one's not really important. But this one right here is, because this is the component along the y-axis. You need all three. You need the x, y, and z components. But if you have beta, you know what that angle is, and you know what the magnitude of this is, well, guess what? You can solve for that y component using cosine is adjacent over hypotenuse. And so that's where our direction cosines come from. We take this angle, which is part of this crazy triangle, and it goes straight to the axis it cares about. And from that, we can get each of our components. Pretty awesome, right? There's a second awesome thing about this. Our direction cosines are actually the components of our unit vector. You're like, what? Okay, so you know that unit vector, that thing that was in the direction of whatever vector you care about? Its magnitude is 1. It's a dimensionless vector that points in the direction that you care about. So this is the way the force is going. It's going that direction. How far? I don't know, but it's going that way. That's what unit vectors are for. Well, each of these things is one of the components of your unit vector. So if you actually know all three of those angles, you can solve for your unit vector. Or vice versa, if you know your unit vector, you can solve for all those angles. And just to make sure that you're correct, you can always check this, because if they don't sum to 1, or if the sum of the squares don't go to 1, it's wrong. You've done something wrong. Because the magnitude of this vector should be 1. It's right here at the bottom you see what I was talking about, where this is our unit vector. So we can write our unit vector as cosine of alpha, cosine of beta, cosine of gamma, where each of those are the angles to the x, y, and then z axis, respectively. So use that. It's extremely, extremely helpful. Okay, now one last thing that's very, very simple and hopefully makes sense is how we add these vectors together. Well, when you're adding together vectors in the Cartesian form, you add all the I components, all the j components, and all the k components separately. So this is only the sum of the forces in the x right here. This is only the sum of the forces in the y, and this is only the sum of the forces that are in the z direction, okay? Do not mix them together. What's great about this is that if you try to, you can actually break it up when you're trying to solve things into 3 equations. I can have one vector equation, or I can break it up into 3 scalar equations for each of these components. This one, and this one. It becomes very helpful later on. So, combining them all together, it looks something like this. I have A, I have B, add them together, they're all together. Or if I'm subtracting them, then I subtract all the components. Okay, so this is the much easier part of this little section, but focus on those cosines, okay? Don't forget your direction cosines. It's a very helpful thing, and I promise you're going to keep on using it for a good 7, 8, 10, 12, 14, 16 weeks. That's here in the summer, then 8 weeks. Okay, so I hope this helps you. Next time we're going to jump into some example problems to really drive this home. So I'll see all of you then. Have a good day. Bye.